Plymouth University, and he's going to talk about Hamiltonian dynamics of degenerate quartets of deep waterways.
Thank you, Henrik. Thank you for coming. Thank you to the organizers as well. It's been a long day, so I think it's fitting to stop or end with something elementary, something simple. And what I want to present is a new approach to a classical problem in water waves. And fittingly, because this is an interdisciplinary workshop here, this is a new approach which has already been applied in the context of optics by Trillo and others, co-workers in the NLS. But I'll show you how it leads to some new and I think interesting perspectives on the Benjamin-Feir instability. So although it is a classical and might be an old problem, I want to connect it to some new ideas, things that are still of current interest. So I'm going to be talking about resonance. And usually we think of resonance as energy exchange. And in the water waves community, there's been some interest in, particularly by Liao and coworkers, in these new steady state resonant and near resonant waves. So how is it that you have resonance but there's no energy exchange? There's also some interest, so this is a recent paper by Waseda and his group in Tokyo, in what phase convergence has to do with modulational instability, both in experiments and in higher order spectrum method simulations. And at some point, I'll also try to connect this idea of phase convergence, modulational instability, and breathers towards the end of the talk. But I want to start at the foundations, at the basics, because this is a water waves talk. And in water waves, we can generate things, and the easiest things that we think about generating are monochromatic, periodic, uniform wave trains. That's because if we don't understand the periodic uniform wave train, it's unlikely we're going to understand other things. So if we test something for ocean engineering, this is the wave that we want to make. So how do we think, or why do we think that this wave is somehow, well, relevant? You flap a paddle, maybe you can make it. How about the equations? Well, the equations that the water waves community usually starts with, certainly the ones that I start with in this context, is incompressible Euler. So written down in 1757 by Euler. Unfortunately, we haven't made a huge amount of progress in finding explicit wavy solutions to these guys. We haven't made a lot of progress in other respects. The problem is really difficult, is what I want to say, because, well, 250 years on, we're still working on it. Yeah? And one of the ways forward, classically, is perturbation analysis. So we expand in a small parameter, and for waves, that parameter is a times k, a being the amplitude and k being the wave number. And this has a good pedigree. If you look at the linearized problem, you throw out all the nonlinear terms, Cauchy and Poisson, so there's around the 1810s, found this linear solution. So we have a uniform periodic wave of constant amplitude with a frequency in deep water, which is omega squared g and then norm k. Yeah? If you're patient, well, you can go to the second order. At order epsilon, you find the same wave. So we think, these periodic waves, they really exist. They're really in there. If you go to the third order, and it took 30 years, Stokes found that also there you've got a periodic wave. But something funny happens, which is this correction to the frequency. And that correction is something that it'll come up again. So a few years after Stokes, Levi-Civita and then also others proved, in fact, rigorously that uniform periodic wave solutions to the Euler equations exist. So we really think that these waves are there. There is such a thing as a uniform periodic wave. We're pretty happy with it. So you generate it. Well, okay, start flapping your paddles at one end of a basin or a tank, and you get something, well, it's looking okay, I think. But then at the other end, it's a mess. And this difficulty repeats itself over and over again. It's very difficult to keep these waves together. So something must be happening, and people realize this, and this is in fact a picture from the experiments of Benjamin-Feir. So if you stick a probe in your tank, and of course this isn't from Benjamin-Feir's experiments, but from other Flume stuff, what you find is, okay, you think you're generating a monochromatic, uniform periodic wave of constant amplitude, but actually you're generating something that there's some junk, there's some noise. And as it propagates down the flume or along the basin, what happens is that the peak, where most of the energy is, shrinks, and the side bands, these guys here, grow. So actually the junk is starting to be amplified. There's also some other stuff which is even worse, which I won't talk about in this, in these 30 minutes. So what's going on here? Well, some kind of instability, right? And how would we capture it? Well, maybe perturbation expansion. If you're very patient, you can perturb and perturb and perturb and keep perturbing. But the problem is now you've got not one mode that you need to perturb, but you've got, well, you saw there's maybe one in the middle and two on the sides. So a carrier and maybe two side bands. And you really have to be pretty patient to do the perturbation analysis. In particular, it's not completely clear what you're looking for initially. So how do we approach the problem? Well, I'll tell you what we can expect on the basis of two very, very simple undergraduate examples. Simple harmonic oscillator with a weakly nonlinear quadratic nonlinearity here. So perturbation analysis tells us at the lowest order we throw away the nonlinear terms, we get solutions e to the plus minus it. And then at the next order, the inhomogeneity there comes from the previous order, right? So on the right-hand side, I get this guy here. And again, it's a forced simple harmonic oscillator, so when you're teaching undergraduates, okay, they expand and then use a favorite method here, I don't know, matching coefficients, and find some solutions. Okay, particular solutions, and then the free solutions. All right, wonderful. So and then you do the same problem. What if there's a cube here, cosmetically completely identical, and yeah, all right, lowest order, since we're throwing this away, I've got those waves, e to the plus minus it. And at the next order, I need to include this guy as a inhomogeneous forcing term, and I expand the cube, and now, well, of course, the undergraduates, then they have to be careful, because of course something is happening here, right? And what's happening is if you try your favorite technique initially, you say, I'm just going to use, I don't know, variation of parameters. Well, there's a forcing that happens to coincide with the free frequency. So what's going on? You get resonance, right? And the same thing happens in water waves. So I showed you before Cauchy and Poisson's solution is a sinusoid. At order 1, that means I've got an e to the I kx plus or plus minus I kx minus omega t. Doesn't matter where the plus or minus signs are. So now at order epsilon, I've got quadratic nonlinearity. So on the right-hand side, as an inhomogeneity, I've got products of two of these things. Those products lead, because a product of exponentials, sum leads to sums like this. So on the right side, I've got something like this, which is the forcing. And if the forcing coincides with a free term on the left, resonance. Things are going to grow. So this resonance happens. Now I need to match not only the k's, but also the omegas. And if I go to a higher order in nonlinearity, which, by the way, these are always weaker and weaker effects in water waves, but higher order nonlinearity, so order epsilon squared, cubic nonlinearity, sums of 3 of these terms, meaning quartets of waves interact. And which of these effects is going to be useful or is going to give us something depends on the dispersion relation. Because I've got a vector sum over the k's, but I also have a sum over the omegas, and omega and k are related now. So the dispersion relation determines the resonance. And this is the crucial thing that was realized by Phillips in 1960. And that set off in the water waves community a huge, surge of effort in this direction. And it tells you what to look for. It tells you, in deep water, you need to go to third order to find something interesting. That's why Stokes, by the way, had to do his expansion up to third order. Because at second order, this resonance doesn't work. It doesn't turn on. So, how do we capture this kind of resonance? Well, here we need to make a little bit of a jump. And the jump that I'm going to make is to the reduced Zakharov equation, which I'm writing in the discrete formulation in this case. That's the way I'm going to use it. But you can replace this integral with, this sum with an integral. You'll be fine. So effectively, what this equation is doing is taking the water wave problem, in Fourier space, expanding to third order, and then there you go. And the variable of interest is this complex amplitude Bn, and it's related to the free surface. That's what I've written in the second term here. So it's related to the free surface by Fourier transform, basically. All of the physics of the water wave problem, this complicated stuff that you would get by perturbation analysis, pages and pages of it, is all contained in a kernel. And that kernel itself is about 2 pages of algebra, depending on the wave numbers. So we've got also a Kronecker delta and a frequency detuning. I don't want to say too much about this, because I think you'll see the salient features in some examples. The first example is, what if you take this equation and you assume there's one mode. There's a single mode in the sea, so in Fourier space there's a spike, and you plug in to this complicated term, all of the sums go over one term. Yeah? It turns out this is the equation, and it has a solution of constant amplitude, and that solution of constant amplitude is Stokes' wave with the frequency correction. The kernel here drops out from 2 pages of algebra to k cubed over 4 pi squared, and whew, you're done. So you recover Stokes' wave. If you put in 2 modes, again, in Fourier space, you get a system. And it turns out that system also has an exact explicit solution for the Zakharov equation, and that is, again, constant amplitude, but frequency correction. And it's the frequency correction that Longuet-Higgins and Phillips, through lots and lots of hard work with perturbation analysis, found. And I think it's, well, I'll mention one other equation, which has gotten a lot of airtime here in this, this conference so far. I need to start now from the continuous Zakharov equation. I haven't written it down. But if you assume there all the sums are integrals and so on, assume the energy is concentrated about a single wave number, and approximate all the interaction coefficients by the Stokes wave interaction coefficients. And then you can rewrite in terms of the envelope amplitude, and you get back Davy-Stewartson or NLS. Or if you care to expand a little bit higher order, you can get Diest equation, modified NLS, and so on. So the Zakharov equation is the parent equation for a lot of these guys, which are narrow bandwidth limits. Yeah. Okay. So we've talked a lot about various equations. What does this have to do with the modulational instability that we started with? The Benjamin-Feir instability of water waves. Well, okay, you can plug that in as well. Now, you may remember that I said in deep water waves interact in quartets. So I need 4 waves, but in that spectral picture that I showed you, it seemed like there were only 3. And the trick is that I need to count 1 twice. And it's not such a bad trick, because in the Stokes wave, I count 1 wave 4 times. In the bichromatic wave case, I count 1 wave twice each. And here I count 1 wave, namely the carrier Ka twice, and the sidebands once. And I'm going to present only the unidirectional case, although bidirectional and so on is analogous. So mode separation will be my parameter P, and we get this system in 3 complex amplitudes. And the typical thing that's been done since the 70s essentially is linearizing this system and finding that what you get for the mode A is Stokes wave, and then modes B and C decouple into a linear system of ODEs for complex amplitudes, and well, you know how to solve linear systems. It's just eigenvalues. Look for the eigenvalues where you get a positive real part, and that gives you instability. And this is the Benjamin-Feir instability criterion from the Zakharov equation. And if you reduce to narrow bandwidth, it gives you the Benjamin-Feir instability criterion for NLS. And we've actually seen this 2√2 thing before, I think 2 days ago in another talk. So if my perturbation wave number divided by the carrier wave number is less than 2√2 times the steepness, we're unstable. Okay, so how good is this linear threshold? Right, we've linearized. Is that any good? And then also, we know the linear theory is good only for a certain time, because things are going to start to grow. You're going to violate the assumptions. So what happens after that growth? Well, what happens formally, the question is easy to answer because you can numerically integrate. You've got a system of ODEs. It turns out you can do better, and you can actually integrate explicitly in terms of Jacobian elliptic functions. And we've known that this kind of thing works for discrete sets of resonant interaction equations since the work of Bretherton and others in the 60s. Both of those are a little bit messy. Numerical integration, because you've got a lot of parameters, and well, classifying the roots of quartic polynomials is not really that fun. Yeah? So you can miss things. And the way not to miss things is to use some insight. And the insight that I want to present to you are, first off, a few conserved quantities for the Zakharov equation, starting with wave action, momentum, and the Hamiltonian for this system, so the energy. And there's a lot of conserved quantities, especially if we've only got 3 modes. It turns out the critical bit is that you can see the Hamiltonian, when rewriting each complex amplitude in terms of magnitude and phase, each resonant interacting set depends only on a single dynamic phase. So 3 complex amplitudes, you'd say 3 phases, but actually no, it's only 1. And then rather than integrating explicitly, what you do is reduce to a planar system. And it's a planar system in 1 dynamic phase and 1 amplitude variable. And you can choose any of the modal amplitudes. I'm going to choose eta, and I'm going to normalize by wave action here. So you get a planar dynamical system, Hamiltonian planar dynamical system of this form. And now you're in business. I'll show you how the business looks. First off, what's the phase space? Okay. There's a few things that I have to choose in this problem. One is wave action, and wave action can be thought of as basically proportional to the steepness of my carrier wave. So choose a carrier with a certain steepness, that's the wave action. And I'll show you the cases where we've got equipartition of energy among the sidebands, but this is effectively everything works if you partition the energy otherwise. Because of conservation of wave action, our variable eta ranges between 0 and 1. So we're on a truncated cylinder. The phase theta goes between minus pi and pi. And the other variable that's going to be interesting here is the mode separation. I'll call that p. So how far away are the sidebands from the carrier? And let's see how this stuff looks. If I'm thinking 1 Stokes wave, conservation of wave action looks like this, and if eta is just the first term right there, eta equals 1 is the Stokes wave. Everything is in the carrier, no sidebands. In the phase plane, I'm up here at eta equals 1. Those are the Stokes waves, that's where they live. They're the monochromatic solutions with, well, the solutions to the Zakharov equation with Stokes correction. Where are the bichromatic waves? Well, if eta equals 0, all the energy is in the sidebands. That's down here on my phase space cylinder. I've unwrapped it, right? Bichromatic waves live down here, and they're those waves, Longuet-Higgins and Phillips waves. Now, what happens with our phase space? Well, we can think about this. Here I've chosen some value. In fact, this is epsilon 0.1 for the carrier wave, so it's a moderately steep wave for water wave standards. And I've chosen here, you can see p is 0.000. So all of the modes are together. The contours here these are the contours of the Hamiltonian in different colors. And the dots are fixed points of the system. The dashed lines are separatrices. I'm going to now move the sidebands apart because this is my sideband separation is the bifurcation parameter. And I notice there's an immediate bifurcation. New fixed points appear in the system. As the sidebands get further and further apart, the fixed points move, as do the separatrices, and another bifurcation appears. A third one occurs now, and then still the sidebands move further and further apart. I see the separatrix starts to contract. Fixed points here move together, eventually coalesce and disappear, And the dynamics is just one of no movement in the energy direction, so energy exchange among the modes, and only movement among the phases. So what are we seeing here? Well, a typical periodic orbit like here, that's what you would get if you ever integrated the Zakharov equation or a related equation. You get energy exchange that looks like this. The modes are fluctuating around. The fixed points, on the other hand, there are still 3 modes active. So but if you numerically integrate at these fixed points, well, they're steady states. So these are the steady state solutions of Liao and coworkers. In this case, steady state degenerate quartets. But in principle and also in practice, this methodology works for real quartets, also for resonant quartets, and in fact for quintets and so on. What about Benjamin-Feir instability, which we started with? Well, the Benjamin-Feir instability is the instability of the monochromatic wave. The monochromatic waves live up here in my phase space. So if I think about one of those waves and I perturb a little bit, I kick a little bit of energy into the sidebands, I see that I'm going to end up on a trajectory here where there's energy exchange. Well, until, that is, the fixed points disappear, in which case, kicking down onto a trajectory here, kicking a little bit of energy into those sidebands, is going to end up on these orbits which flatten out progressively. So what's Benjamin-Feir instability? Well, it's effectively, for the Zakharov equation, it's this dark shaded region. The plots that we've got here are for epsilon 0.1, and we see as I move my mode separation to 0.25, here I exit the stability region, the waves stabilize. So the plane wave, the carrier wave, stabilizes. The slightly lighter shaded region is the NLS instability domain, just for comparison. You can see that there's some qualitative differences. And in fact, if you wanted to get quantitative, you would find that the criterion, the analytic criterion for the appearance of fixed points is exactly the same as the linear stability criterion that I showed you a few slides ago for Zakharov's equation. So I'll try and wrap up. There are a few more interesting things, such as what's happening on those separatrices. Well, a separatrix connects plane wave to plane wave via a modulated wave. And here at the top, you see the envelope, and here this is the actual free surface written in dimensionless coordinates. So we're looking at a plane wave at one of these fixed points. And then as we move along the separatrix, we've got a modulated wave. And we move back to a plane wave up here with a phase shift. The envelope is up here, and I think, well, many people might recognize this as something that looks like an Akhmediev breather. In fact, this is a primitive type of Akhmediev breather. You can play the same game for the separatrices on the other side. These are separatrices connecting bichromatic waves to bichromatic waves via some kind of trichromatic wave. And, well, the envelope is a little bit messier. And, of course, there's a special case when they connect, which has also been observed for NLS by Capellini and Trello, where you've got effectively a monochromatic to bichromatic transition, or vice versa. And you can write these analytically for the Zakharov equation, get these kinds of new breather solutions. Okay, so what's the take-home message? Quartet and quintet interactions in deep water are integrable in terms of Jacobian elliptic functions. But my advice, if you need to do this, is don't classify the roots of polynomials. Instead, do something better, namely use the structure of these equations as planar Hamiltonian dynamical systems to get really a fantastic amount of insight into the problems. You can identify the periodic orbits and, in fact, also the role of phase coherence in the problem. You can find new and explicit breather solutions of the Zakharov equation and see the role of these steady-state quartets and steady-state quintets, which have been found by other methods by Liao and collaborators. And, of course, you can classify instabilities without the need for linearization. So there's some more details on the archive, but I think that's it for me. So thank you very much for your attention.
Thanks very much. Any questions? Yeah, Panos? We have just time for a couple of questions because the tech support has to shut down, but we can keep the discussion going after the system is shut down.
So you talked about the AEM. The natural question is the Mediev breather. What about the KEM and the peregrine?
So peregrine breather, I don't know, but here we've got so I've written down the Zakharov equation as the usual temporal evolution equation. So this means that the breathers that we're going to get out are Akhmediev type breathers, which are periodic in space and breathe once in time. There's a corresponding spatial Zakharov equation derived by Lev Shemer, Kitz, Jiao, and Agnon in the early 2000s. And the same kind of techniques work for the spatial Zakharov equation. It's just a matter of rewriting things in that frame. Peregrine, I'm not sure. It's a good question and something to look into. Yeah. Or peregrine type, I should say. I mean, yeah.
Okay, very good. Yes?
Just comment. So you might find some analogy in nonlinear optics. So with parametric amplification, so where you have some pump, plane wave in your terms, and then energy is transferred either initially to 2 sidebands. You can also consider 5 and 7. So it's quite actually technique which is used in fiber. So it's a very interesting connection here.
So I think a lot of this work perhaps has been done. It was certainly initiated in optics, looking at the NLS by Stefano Trillo, Wabnitz, and Capellini. I think were co-authors on the early papers in the 90s. So thank you for this comment. I don't know about extensions. So once we start to get more and more modes, you.
Temporal domain, it's the same. But when you move, but you have different special stuff. So that I'm not saying that everything was done. I'm saying you can take something and actually create quite nice new solutions for your case. They will be different from
Yes, and I think so the Zakharov equation formulation in principle encapsulates NLS. So the full, or taking into account the full interaction kernels, gives some different physics, which is relevant for the water wave case. But thank you for the comment.
Maybe I can
of course. Yeah.